Hello, Sasha.
Hello, Oliver.
Sasha is our expert on powertrain durability and NVH, and with it, he is responsible for all the structure dynamic application and contact evaluation, and with this, responsible for EXCITE M as a product. And I'm curious, what's new here? We talked the last time a lot about introducing the ICE modeling capabilities into EXCITE M, and you promised that there are new things coming up also for ICE. What's new now in this 2024 R1 release?
Thank you, Oliver. Yes, we are adding new capabilities, and one maybe interesting new capability that we added a belt connection in EXCITE M, which means we can now connect pulleys with the belt. It can be looked at as accessory belt or as a timing belt. We had such a capability in EXCITE Power Unit, but now the usability is improved. User can easily define the pulleys, the characteristic information on the stiffness and damping of the belt spans. So this would be rather useful for instance, hybrid applications where you have start-stop system belt-driven.
Yeah, when we stay with the ICE engine, very important are also the EHD contacts, which we have there, the slider bearing, piston contact. Also, this is new in EXCITE M, and also here I assume that there are updates with this release.
Yes, we released, as we remember, last event, we released elastohydrodynamic capabilities in EXCITE M. And especially for EXCITE M, we now developed a wear workflow, which enables to predict the wearing in process, also enables to determine the more or less the lifetime of the bearing or the amount of wear after a certain operation time. The wear app actually is running sequentially, meaning or you can have it as a step approach where you calculate first the starting with the perfect surface of the bearing, and then based on the asperity contact pressure, the wear amount is calculated, and then with this new shape of the bearing, you come to the next step. As I mentioned, the sequential work or the sequential way of thinking is typically when you want to reproduce a measurement of the wearing in process. And another option where we have accumulated wear over a different operating conditions would be something more for targeting real life prediction of the wear after a certain operating time. So in the example shown in the graphs, we have seen wear depth after several steps, and starting from a perfect surface where we see some stronger asperity contact, especially on the edges, which will then lead to a certain wear. And then we go from this worn shape to the next step, where we then see some wear accumulated on the edges on the surface, while the asperity contact is reducing. And in this particular example, we have seen that after 6-7 steps, the amount of asperity contact is very low, and we have reached a certain wearing in process.
So I understand correctly, we are not only investigating the wear profile, how it develops, but how the bearing at the end operates under worn condition and how the behavior changes.
Exactly.
Yeah, switching now from the ICE to the eDrive system. So this was the first implemented application in EXCITE M. I heard also there is something new which you can report.
Yes. We continue on transferring the capabilities which we had in EXCITE Power Unit. One of these was the so-called electromechanical coupling joint. So it's now possible to transfer electromechanical coupling joints from EXCITE Power Unit to EXCITE M. So all people who have the models in EXCITE Power Unit with this type of joint are now, let's say, with the click of a button, can transfer them to EXCITE M. Another advantage when you have such a joint in EXCITE M is that in the controller, you can have we have a predefined controller where user can define some parameters, but we allow also coupling of real controllers like MATLAB, developed in MATLAB, and then you can couple this into our EXCITE M e-motor joint directly, so that practically EXCITE model will run in co-simulation with MATLAB, or will have it as an FMU coupled and would run in this environment.
So this modular approach allows now more flexibility. I understand different components can be replaced, and not only the built-in capabilities can be used, but
Yes.
as I understand, you can replace by user-defined components.
Exactly. In the old joint, for instance, on the inverter side, we had always ideal inverter, and now we have a possibility to replace this ideal inverter with user-specified inverter. We also have a very smooth guidance with view parameters. You can specify really realistic inverters, which will then influence the current which is reaching the e-motor or this e-motor joint in EXCITE, and will then lead to another NVH response of the e-motor, because the excitation forces are calculated directly in EXCITE, and this is really unique feature of EXCITE.
Okay.
On the
so
market.
it goes now really deeper also to consider pulse width modulation and really the behavior of the inverter itself and the influence.
Exactly. You can vary then the frequency of pulse width modulation, you can vary the type and so on.
Yeah, I understand also this EMC joint allows also not just stationary condition, but also transient condition. And I heard you have an example where you demonstrate what's possible now.
Exactly. So transient conditions are really interesting. An example, for instance, where e-motor changes torque, shown on the graph. And in the animation, we can see how this actually happens. And in the picture, we can see also the impact forces in the gears when the torque has changed. And the engineer can judge about the level of impact from the durability point of view, for instance. But how much will this impact influence the NVH is also a question. We can look at the accelerometer results and see certain jump in the acceleration, but it is very difficult to judge the frequency content of such impact. And for this, now we have introduced so-called velvet transform or velvet transformation of a virtual result, in this case of the virtual accelerometer. So you can now track in time domain what is the frequency content of the excitation, or let's say response, and you can track also the level of this frequency content. And this is something which is typically used in the measurement.
Yeah, very interesting to have this compressed together in one view to get really the insight into a whole maneuver, not looking at different plots, but having all of this together, a transient maneuver and the frequency NVH content in one graph.
That is, I think, also a unique feature for the softwares.
Yeah. Staying with the e-motor and the e-drive, it's always a topic to rise up the speed of the e-motor, to go to high-speed e-drive systems. And of course, things which are very important there are shaft balancing, asymmetries, and things like that. So there's also something new regarding rotor modeling.
Yeah? Yes. So typically, rotors are modeled using finite element models, and these finite element models are quite often, let's say, perfect, so you don't have any unbalance. But we know in the real life production, there is always some unbalance or some residual unbalance. And in order to consider this unbalance, you would have to do it either in the finite element model, perform the condensation, and perform then EXCITE simulation to see the influence of unbalance. This is really cumbersome. And what we did here is to introduce automatic unbalancing, so the user can specify unbalanced mass anywhere on the finite element model, and this unbalanced mass will be considered then in the dynamic simulation. So no need to new FE model, no need for new condensation.
So it's fully considered in the full dynamic, which is not so easy. It's not just statically, it's also for the gyroscopic effect, uncondensed mathematics and everything. So it's adapted in the whole.
Like you did it in the FE model, but you just don't do it in the FE model.
Perfect. Yeah, another topic which is always when we're talking about e-motor is different types of e-motor. Is there anything new regarding coverage of new e-motor types
Yes.
or anything new
Yes,
to report?
we actually can cover to all this extent what I mentioned, a permanent magnet synchronous machine. From this release, we will be able to cover also externally excited synchronous machines. So here the limitation will stay that we cannot cover the eccentricity because we have additional parameter, and that's the current on the rotor. And I can already give an outlook for the upcoming release. We will be able to consider also induction motor with this type of approach, again without the eccentricity, but all the other effects are considered.
Yeah, with that, thanks a lot, Sasha, for joining, and thanks a lot for introducing the news in your solution area to our users.
Thank you very much, Oliver. Thank you.